Assalamualaikum and a very good day everyone. Today we will presenting our flash separation analysis for a binary mixture of ethanol and chloroform. While this system is highly non-ideal and forms an azeotrope in reality, we are modeling a single-stage flash using an ideal solution assumption. This establishes a baseline before factoring in non-ideal deviation. Our goals are to analyze the system's vapor-liquid equilibrium, identify the optimal operating conditions, and determine the final phase composition and flow rates. We use Rolle's law to define our equilibrium K value, calculating component saturation pressure via the Antoine equation. This ratio was then applied to the Rashford equation to solve for the vaporized feed fraction. We evaluated three cases. Case A at the bubble point, 67.8 degrees Celsius, case C at the dew point, 70.4 degrees Celsius, and case B at 69.1 degrees Celsius. Our feed is 100 mol per hour at 40% of ethanol and 60% of chloroform, giving us a stable 2.6 degrees Celsius operating window clear of the azeotrope. The flash drum is modeled as a steady-state single-stage separator. We assume instantaneous phase equilibrium, zero enrichment or carryover, and an activity coefficient of exactly 1. Our main task is to calculate 4 key variables: the total moles of liquid and vapor, and the specific mole fraction for both phases. Our workflow follows this step. First, initialize inputs and find saturation pressure. Second, calculate bubble and dew points to confirm the two-phase region. Third, use Rolle's law for K values and phase composition. And finally, solve the Rashford-Rice equation for exit flow rates. All Antoine constant and physical coefficient were sourced from Appendix B of our thermodynamic textbook.
So for case 1 at 67.8 degrees C, our Antoine calculation yield a bubble point of 101.7 kPa and a dew point of 92.3 kPa. So we can confirm the system is inside the two-phase region. So for case 1, K value and composition chloroform show a strong preference for vapor with a K value of 1.24. However, the Rashford-Rice equation revealed only 4% of our feed has actually vaporized. Molar flow rate, this leaves us with a high liquid flow rate, with a high liquid flow of 95.7 mol per hour and a tiny vapor stream, while this loop temperature yields high purity vapor. The actual production volume is far too low for commercial use. So for case 2, pressure and phase boundary, we raise the temperature by just 1.3 degrees C to 69.1 degrees C. This shift our phase boundary upward, lifting the bubble point to 106.3 kPa and the dew point to 96.9 K value and vapor fraction. The added heat drive more volatile chloroform into the vapor at 66.8%, leaving behind an ethanol-enriched liquid phase. Solving Rashford-Rice give a vapor fraction of 0.54. We successfully vaporize over half the feed. So molar flow rate, this yields a balanced split 54.4 mol per hour of vapor, high component enrichment, and excellent volume. Case 2 is then considered the optimal operating condition. For case 3, pressure and phase boundary, we push the temperature to 70.4 degrees C. The system dew point calculated to 101.6 kPa. Since our operating pressure is now below this threshold, the system is actively exiting the two-phase region. So K value and vapor fraction, here the Rashford-Rice equation yields a mathematical vapor fraction of 1.03. Because a physical fraction cannot exceed 100%, we bound this value to 1, signifying complete vaporization. Molar flow rate and phase interpretation, liquid flow dropped to 0 and the entire 1 mol per hour feed exit as vapor. So with no liquid phase left to separate the components, the composition simply reverts to the original feed mix. The flash drum has officially ceased to function as a separator.
Our summary confirms chloroform as a highly volatile component, with a K value consistently above 1. As temperature rises from case 1 to case 3, the liquid ethanol fraction climbs from 40% to 55%, proving that the remaining liquid becomes more concentrated with heavier components. Look at this 2.6 degrees increment where the system transitions from 0 to 100% vaporization. For industrial operators, this extreme sensitivity means that even a small 1 degree fluctuation can completely disrupt the product streams. This plot tracks liquid ethanol depletion. Near the bubble point, we retain and recover almost all of our ethanol in liquid phase. But as we approach 70.4 degrees Celsius limit, that recovery drops to zero as the ethanol is forced to vaporize. Conversely, vapor flow increases with temperature. While maximizing vapor volume may seem ideal, it creates a critical trade off. At 100% vaporization, we lose our purity advantage, and the output simply reverts to the original unseparated feed. This shows the engineering trade-off between purity and yield. Case 1 gives high purity but very low volume. Case 3 gives maximum volume but no separation. Hence, case 2 is an optimized, balanced middle ground. To wrap up, we successfully modeled the binary flash separation. Case 2 at 69.1 degrees Celsius is the optimal design point for balanced product split, proving that temperature is a critical control variable within this highly sensitive operating window. Our design was supported using foundational data from Smith, Vaness, Abbott, Kim Lang, and Yu. That is the end of our presentation. Thank you for listening.